Physics。他送我啊，他送我。
啥呢？
不拿白不拿。
好。8点了。你不知道他这个辛苦的吗？OK， 其实你说，从这个，你可以按好这边是 X 我就 K 啊。UX 啊，negative differentiate UX 不是？negative 什么 ？X 哦，好难。不过挺吃的，很好难的。那个是我知道的那个，那给你给过的。我找他说嘛是嘛，我就要他嘛，不是啊，一直到一直都给他。我知道就是。
啊，
人家给哦，不拿白
很好，谢谢你，谢谢你。
哦，给 right 哦，
学校的网有问题的，学校的网有问题。啊？我的 lecture note upload 不到。
还差一点点，就一点点。
啊？没事没事，没有问题。
哎，他
啊？谁？
我的 N 哦，
啊哈？
他的 confidence action 哦。
啊？
就是顺便，莉迪亚刚刚一直在吐槽你写的好丑。
哪个？哪个？哪个？忘记。
他觉得你的 notes 写的很丑。
哦。调啊，可以调啊。
这怎么调？
我不懂哦。
我觉得现在比较合适。
研究一下调啊。
这样要调哦，
研究一下，等下研究一下。
我觉得不用。
没有，我给你看过啊。
什么？
那个 before v space 和 after v space 嘛，就是它的 definition page。
哦，那个可以整个调啊，那整个直接调啊。
我现在就还是这个东西没
那
动。
text height 直接调罢了。
这个东西我让。
然后用那个 layout。
对啊 ，text height 直接调掉。
稍微少写点这种样子，你不觉得这种需要用图画去描述，很烦哎？
啊？怎么办呢？ reduce 一点 resolution 也可以。你 try 看 reduce 一点看。等下我们再看一下。Testing。Alright, hello, testing. Okay, good afternoon to everyone. How about let's start, and then maybe we can take a break after 1 hour. No. I mean after 1 hour we'll break for 10 minutes. Let's start first. Alright. So let's recall what we did last lecture. Okay, let's recall what we did last lecture from a previous lecture. So in your mind, you cannot forget what is the definition of group. Okay, you can never forget. So what do you have in group again? Yeah. So you have associative LT, right? Then identity, then inverses. Okay, so typically your group is non-abelian. Okay, typically it's not. Although the number system you learn are all abelian, right? But typically it's not. But inside this non-abelian group, you can find a abelian group, right? So what are those abelian group you can find? For example, cyclic subgroup. Okay, cyclic subgroup are abelian. What else? What else I taught you last time? What group are abelian? What subgroup are abelian? I ask you go back and prove, right? Which are the center? Okay, maybe not all of them will commute with each other, but center will. Okay, and if you collect all these center together, they form a abelian subgroup also. Okay. What are the special thing about cyclic subgroup? If you go further into the subgroup, it is still abelian, and not just abelian, it is still cyclic. Okay, so if you go deep into cyclic subgroup, it's just cyclic subgroup again. There's nothing special about cyclic subgroup. Okay, so we have cyclic subgroup center, and then one more subgroup I taught you, right, last lecture, which is the normal subgroup. So what's the definition, equivalent definition of normal subgroup? Let's call this N. N to satisfy what? Gn equals to N G for all G in G. So what's G here? So G is the original group. Okay, this means what? This means that this normal subgroup is almost a center, almost. Just that when you do G little n, it won't go back to the same little ng. Okay, maybe Gn1 equals to n2g. Okay, this is what it means by the equality of set here. Okay, it will be the case. So let me make it greater. So for example, Gn1 equals to n2g. Okay, where n1 not equals to n2. So you can see that center is a specific example of normal subgroup, right? Okay, because if you consider this center to be Z, obviously Gz equals to Zg for all G equal to G. Okay. But this equality here is on the north. Okay, on the north. So what do we mean by on the north here? So if you take Gz1, it has to be equal to Z1G. Okay, on the north. Okay, on the north. So the equality here is on the north. Okay, if you check set, so let me specify here. Here is about set equality here. The other one is about element. Okay, so remind you this equality, you have to ask yourself what kind of equality. Okay. As a set equality, you can commute. Okay, but if it's center, this set equality here is on the nose. Okay, so my pace maybe will increase a bit comparing on the first few lecture. But you feel free to stop me if I go too fast. Okay, feel free to stop me. Too slow. Too slow. Depends. It will depends. It depends. Okay, so we are a democratic country. Okay, you can voice up. You can voice up, but we will consider. Okay, so we are a democratic country. So you can voice up, we can consider. But if sorry, yeah. So if you worry that your question is too trivial, your worry is correct. Your worry is correct. Okay, but I treat you as a pure maths baby. Okay, baby. What happened to baby? Okay. One thing is about baby crying. How about the other thing? Maybe baby poop. You know what is poop? Yeah, 大便. So maybe poop, he don't know how to clean himself. So need parents to clean for the baby first. But now, if you poop, did you need your parents to clean for you or not? No. More than no, right? You will feel ashamed. Then you do it yourself. Okay or not? So similar now. Okay, you are a pure maths baby. You have trivial question. You ask first, I help you clean week 2, week 3, week 5, week 7, week 8. You have to clean yourself already. Okay or not? Understand? So we have to grow up. Okay, we have to grow up. No choice. This because the university is like that. Right. Your high school study for 1 year, right? But university is semester by semester. So you have to grow very quick. Yeah. Very quick. It's like that one. Every year after I study, after year by year, my mentality change one. After every sem, every year, my mentality change. So you have to grow up. Okay? So it's about growing up. So my supervisor once says, there's no hard mathematics question. It's just that you are not mature enough to understand it. Once you are mature, you will see, not that hard. Oh. Yeah, so you have to grow mature. Go mature. Growing mature is very important in mathematics. Okay? Right. Is it clear or not? So feel free to ask now, because maybe no one help you to clean your poop next time already. Pure maths poops. Okay, so now I can help you clean. Yeah. Hey, my student follow me for 3 sems. They grow very fast. Third sem, they only need me to clean already. Maybe they clean for me already. Seriously. So like I have a 5 FYP now, right? So we communicate, we ask each other question. I help him to solve his problem. He helped me to solve my problem. Then we solve each other problem. This is how it works in adult world. Okay, it's not by threatening, scoring, or what. We by discussion. Okay, healthy conversation. Okay, everyone want to do good. So no need to how to say be picky or what say bad thing bad word nothing like that. Right. Okay. Understand? Okay, so feel free to ask now, but slowly you need to grow. Okay, you need to grow up. Then later you have to settle yourself. Okay. Right. There's one more subgroup in the group G you can consider, right? Let's say if you have a map out from the subgroup G, a homomorphism here, what do you have? You will have a kernel of this guy. Okay, so this kernel may be trivial. If it is trivial, then say meaning what? This map is injective. Okay, if it is not trivial, then this map is not injective. Okay, this is why this kernel is good. It is still a subgroup. Okay, so you have kind of seen quite a lot of structure inside group already. So today we're gonna learn a special homomorphism here, which is called the isomorphism. Okay, so what's an isomorphism here? I Hansing changed my thickness again. Too thick. So
Yeah, take a-
okay, so what's an isomorphism here? So an isomorphism from G to G prime, domain G to codomain G prime, two groups, is a bijective group homomorphism. Okay, so we just consider a bijective map, which is a homomorphism. Okay. So two things, there are two things here. So let me break out the two things here for you. So first is a bijective map. You know what a bijective map is? What? What is it? One to one and on to. Good. Injective and surjective. Second, it has to satisfy the homomorphism property here, such that Vxy equals to Vx times Vy. Excuse you. Okay. Right. So what are the examples of isomorphism? Let me give you an example. Later we'll prove that it is a isomorphism. Okay. So meaning what? Isomorphism is a set or is a function here? Function is a function. So you need to define a function. So what function is a isomorphism here? For example, the exponential function. Okay, from r plus to r cross. But we need to restrict this r cross such that it is greater than 0. Thank you. Right. So this is the isomorphism. And let me give you two more. So the other one is Z to a cyclic group. Okay, this cyclic group has no finite order. Okay, so you can continue to add. So let's say A has no finite order. And to A to the order. And then the third thing is the one that you see in your assignment or we introduced in class before, which is Sn to, let's call it Pn. Okay, Pn live in GLN, where this Pn is defined to be the set of permutation matrix. Okay, soon we will try and compute C1. All right. I want to talk before I talk about the real isomorphism map. Let's talk about this first example here. Okay, how do you imagine this exponential function? How do you imagine? When I ask you to imagine, right, you really need to draw something out. Okay, need to draw something. So how to draw an exponential function? You know how to sketch it? Huh? So in calculus, right, you will draw something like this, right? Okay. Right. So how about you draw this real number as a real line? And then what's this r cross greater than 0? This is the positive real number like this. Okay. So, I mean, if you get rid of these s's, right? So what did you see here? So you are trying to map real line to this, let me draw it, to this half line. Okay, let's call it a half line. Right. So what happens here? What really happens here? You are trying to stretch this half line in an EX way. Does it make sense or not? Does it make sense to you? Sense to you or not? So I mean, let me think how to explain to you. So let us move this way. So you start with a real number, right? Okay. So this real number has no boundary. Okay, go to infinity, negative infinity. But what is e to the r here? What's the image? Right? What's the image of this map? So the image of this map is, if you put in the graph, it looks like this. Okay. So can you imagine you are somewhat bending this y-axis here? Can you imagine? Imagine. Can you imagine like you bring this straight line here, you kind of bend it. Okay. Okay. But where these values come from? These values are come from this half line here. Why? Because you learn in high school that the asymptote of this graph is 0. So we don't take this point. Okay, but every point away from 0, you take it. Okay, does it make sense? Okay. Okay, so I mean, later we'll use the algebraic way to verify this. Okay. Any questions so far? Yeah. Good. So next, to verify it, we will use this nice lemma here. We'll introduce a nice lemma here. So the lemma here is, if phi is an isomorphism, then the inverse of this map is automatically a isomorphism. Okay. So this lemma is good. How is it good? If you can never find an inverse of your isomorphism, you no need to check whether it is a group homomorphism already. Okay, it will automatically satisfy. I'm going to prove to you. So this is what this lemma about. So if you have an isomorphism, the inverse map, if you can find the inverse map, is already an isomorphism. So you just need to prove to me the inverse property. Then the group homomorphism property will automatically satisfy. So I'm going to prove to you now, okay, for general group isomorphism. So let's prove this. So what do we gonna show? So suppose phi is an isomorphism. Okay, what do we want to show here? Then what? We want to show that phi inverse is an isomorphism. Okay, so isomorphism got how many property? One, bijective map. Second, group homomorphism. Obviously, if we have produced this inverse map, right, we know that phi inverse is invertible, right? Who is the inverse of phi inverse? Phi. Okay, phi is the inverse of phi inverse. And last time I proved as a lemma, right? If it is invertible, it means that phi inverse is bijective. Okay, you can take for granted also can. Okay, if you forget the proof, you also can take for granted. Function being invertible, meaning if and only if function is bijective. You can take for granted if you like. But I also produce a proof inside the notes. I think lecture something 6, 5, somewhere there. Okay. Otherwise, you take for granted. It's fine. Okay. If it is invertible, then it is a bijection. For function, don't confuse. Don't confuse with general invertibility of group element. This is for function. Okay, so I write here function. Function. Okay, so this is automatically satisfied. So the next non-trivial thing to show is we want to show that phi inverse is a group homomorphism. Okay, why is it a group homomorphism? So to check group homomorphism, what do you need to check? Phi inverse of AB equals to phi inverse A, phi inverse B. Where do I take this AB from? What's the domain of phi inverse in this case? G or G prime? G prime, right? Because G go from G to G inverse, so the inverse should go from G prime to G. Okay, so let's take two elements in the codomain. So take AB inside G prime. So what do we need to show then? In turn, we will show the inverse of AB equals to phi inverse A dot phi inverse B. Okay. So again, you see, start from lecture 1 until lecture how many 10 already, we are still showing two things are equal. So it's really similar strategy, but you need to use different property here. So what sort of property we can use here? So either you can go from left to right or right to left or anywhere you want to go. Okay, so what can we use here? What information we have? We have very few information only. Okay, we have very few information only. What do we know? We know that phi is an isomorphism. So how phi behave with phi inverse? What do you get? Phi inverse. Identity. So maybe you can try and play around with it, right? You can play around with it. So no. If we apply phi inverse AB, what do we get? We get AB. Okay. But this is not what you want, right? You want something else, right? If you want to apply phi on both sides, what do you get? You need to produce these terms. Right? You need to produce this. Okay, not just this, but phi inverse A, phi inverse B. Is it possible or not? Is it possible? You consider the original equation here. So how does this compare with the original equation if you apply phi on both sides? But if phi apply on this whole thing is what? I can split. I can split. But after I split, what is it? What is it? It is just A times B. Okay, so maybe we can do phi inverse on A, right? Identity on A. And phi inverse on B again. Okay. And then we can try and pull it out. So we can try and pull it out like this using homomorphism again. Okay, but does this help or not? What we want to show is the two inside things are equal. Correct or not? Can we deduce that the two things inside is equal? How? How? Can we deduce two things inside is equal? Huh? Bijective? Who is bijective here? B is bijective. Not what's the main property that you can use to deduce? 1-to-1, right? Because phi of x equals to phi of y will imply x equals to y if the function is is injective. Okay, since phi is injective, we see that phi inverse of AB equals to phi inverse A times phi inverse. Cannot. Okay. So if a function is injective, meaning what? If the two image is the same, they must come from the same pre-image. Yeah. Any question? Any question? Following? Okay. So this is about why the inverse map of group homomorphism has to be a group homomorphism. Okay, what have we used? We just use that. We just use what? We just use phi, the group homomorphism property of phi and injectivity of phi will give us what we want for what we want to show for the inverse of phi to be group homomorphism. So the inverse map being group homomorphism come from phi. Does it make sense? Okay, so in future, once you have isomorphism, then the inverse will be automatically isomorphism also. All right. So let's define some more thing. So we'll say that two groups, G and G prime, are isomorphic. Okay, are isomorphic if there exists an isomorphism P in between G and G prime. Okay, so this isomorphics is referring to two groups. Okay, but how to get two groups to be isomorphic? You need to find an isomorphism. You need to find a map. Okay, when you want to talk about two things the same, you need to find a map between them. Do you agree or not? Do you agree or not? Do you agree or not? Okay. It's like when you want to talk about two person is the same, right? For example, Yun Xi and Yifan are the same. What's the similarity here? Through what? Gender. Okay, for example, gender. Okay, gender is your map. What else? Maybe they wear spec. 戴眼镜。什么？你说什么？戴眼镜。Okay, yeah. Okay or not? So you need to find what's the map between them. Okay. So introduce some notation here. If G is isomorphic, G prime, we will denote G tilde equal to G prime. Okay, tree line. Okay, this is an isomorphism. So let me put a remark here. So isomorphic group. So I mean, wait, let me think. So isomorphism between groups is an equivalence relation. Okay, try and prove this. Okay, so I put this as an exercise. Prove that isomorphism between group is an equivalence relation. Okay, so think about, I don't want to write down, but I will tell you the idea. So what's the equivalence relation is? Equivalence relation includes what? Reflexivity, symmetric, and transitive. So you ask yourself, is a group isomorphic to itself or not? If it's isomorphic to itself, can you find an isomorphism between them or not? What is the isomorphism you can find between a group and itself? What's the map you can find between G and G, which is an isomorphism? Huh? Identity. Just use identity map. And identity map, what's the inverse of identity map? Itself again. It's easily a homomorphism. Okay, identity map. So symmetric says what? If G is isomorphic to G prime, is it G prime isomorphic to G or not? Why? If you have an isomorphism from G to G prime, what is the isomorphism from G prime to G? You just take the inverse, and I just proved that the inverse is still an isomorphism. Okay. Transitive, if G is isomorphic to G prime, and G prime is isomorphic to G prime prime, is G isomorphic to G prime prime? Why? You just compose the two isomorphisms together. So in turn, you need to prove that composite of isomorphism is still a isomorphism. Composite of bijective function is still bijective. Composite of group homomorphism is still a group homomorphism. Okay, but these are easy exercises. Okay, you should try it out. Okay, so in this case here, we will form equivalence class here. Okay, so an isomorphic class of G is a set of groups that are isomorphic to G. Okay, that are isomorphic to G. Okay, so this is a general abstract nonsense that you get from equivalence relation. So once you have an equivalence relation, you will form equivalent class. Okay, so this equivalent class here is called isomorphism class. Okay, so meaning inside this class of G, the representative G here, everyone has isomorphism to this G. Okay, equivalent class. Okay. Right. Time is it? Okay, we still have time. Any questions so far? Any question? Okay, so far. Okay. How about I give you some example, but I don't prove to you yet. Soon or later, we'll see these example again. So one example is every group of prime order P is cyclic. Okay. In other words, all groups of prime P is isomorphic. Okay, isomorphic to a cyclic group. So all groups of order P is isomorphic. So do you still remember what does it mean by order of a group? Yes, number of elements. Again, number of elements. Don't confuse with the order of an element. So order have two kind of usage here. So this is order of a group. So it's a cardinality. Okay. So if the group have order, prime order, it is cyclic. In other words, they are all isomorphic to a cyclic group. Can you imagine a cyclic group with order P? Cyclic group with order P. ZP. Okay, ZP. Okay, 0, 1, 2, 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 7, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. I think some of them I mentioned too many. Too many by one. Okay. 0, 1, sorry, 0, 1 got two elements, right? And then 0, 1, 2 got 3 elements. 0, 1, 2, 3, 4 got 5 elements. 0, 1, 2, 3, 4, 5, 6 got 7. Okay. Okay, so they form isomorphism classes. This one we will prove later when we go to when we see Lagrange theorem. Okay, later when we see Lagrange theorem, we will meet this statement. So okay, something I won't prove to you. You can keep inside your storage first. Later we will take it out again. Just that I want to give you some context. Two is there are only two isomorphism classes of order 4. Okay. Order 4. Okay. So actually I proved existence for you last time. Okay, so existence was I gave you Z4 plus and Z2 cross Z2, and then we use plus also. Okay, so later, I think hopefully later I'll show you they are not isomorphic. Okay, and why in this world there's only two of them? We have to leave to later also. So I've shown you existent, there are two kinds of them, and then later I'll show you that they are different, they are not isomorphic. And then one thing left to show is in this world there's only two of them. There is no other thing. All other order 4 element have order 4 group have to reduce to these two. Okay, that one also have to leave to Lagrange theorem, I think. And last one, which I won't discuss, is there are 5 isomorphism classes of groups of order 12. So you might think, how on earth I will prove this kind of thing? So if my group has 12 things, why only 5 way I can put my LC? Why there are only 5 way I can put my LC? How on earth to prove these things? Actually, I think Artin use geometry. So if you're interested, you can go to Artin 7.8.1. I think we have no chance to met in this class. Okay, if you are interested, you can go ahead study. Okay, but first two, I guess we can expand later using what we learned. So these are coming soon. Okay, should we learn to prove some two group are isomorphic? So let's do some concrete example. Okay, let's do some concrete example. So for example, let's prove some easy statement here. So prove that the group generated by 1, 2 is isomorphic to the group generated by 2, 3. Okay. So what can you see from these two? I mean, what is 1, 2 here? I can really see it as S2. Really? 1, 2. 1, 2 inside the group generated by 1, 2 is what? 1, 2 and identity, which is S2. You permute 2 indexes. But this guy only also have 2 elements here, identity and 2, 3. So this is a subgroup inside where? Inside S3. Good. So in principle, these two sets is not the same. Correct or not? Not the same. Commute different thing. Element wise, when I say not the same, I mean set wise. Element wise, they are not the same. Okay? The set elements in the set is not the same. But I want to say that they are isomorphic. So meaning what? There is a map. What map is that? It is a group homomorphism, and it is a bijective map. Okay, so I'm going to build this map. So to build this map, right, you need to tell me where the elements go, correct or not? Okay, so you need to build a map between these two sets here. I mean, there are really few ways you can map them, right? If you want to satisfy a group homomorphism. What does group homomorphism tells you? You need to send what to what? Property. Huh? Sorry? Identity have to go to identity if you are a group homomorphism. So if you want to satisfy group homomorphism property, it has to send identity to identity. Then there's no way to send 1, 2 to other place. So the one way to define is have to send 1, 2 to 2, 3. So now you need to prove that this is a homomorphism. Okay, so you need to check this is a homomorphism or not. How do you check? For every xy in x2, you need to check that phi of xy equals to phi x times phi y. Okay. But in this case, how to check? I define phi on elements. So we really have to do it brute force. So by brute force, do you know what brute force means? So in mathematics, brute force here, we will check on every possible combination. Okay, we'll check for all possible combination. Luckily, there's only 2 elements here to compose, right? So there are at most how many possibilities? 4. Okay, so you need to check whether 4 equations satisfy. So what are the 4 possibilities? Phi EE, Phi E12, Phi 12 E, and then Phi 12 12. Okay. And then on the other side, what do you want? You want that Phi, Phi E times Phi E times Phi E, and then Phi E times Phi 12, and then Phi 12 times Phi E, and then Phi 12 Phi 12. Correct. So do you know how to compose elements in S2 or not? You know, right? So what is EE? EEE. Okay. E12 is what? Phi on 12, and then 12E also the same. And then 12 times 12 is E. Okay. So where do we send E to? We send E to E. C122, 23. 122, 23. E to E. So is it equals? So let's do the first one. E equals to what? E dot E. Second, E23 equals to what? E dot 23. Similarly, we get 23 dot E. And then equals to 23 dot 23. So you can see that we have really used property of identity and also use the inverse property. Yeah. Does it make sense? Okay. So this is about group homomorphism. So here, so V is a group homomorphism. How to show this is a bijective function? How to show this is bijective? How to show this is bijective? What do you need to check for bijective? There are few ways to do this actually. Okay, to show bijection. There are few ways. Okay, so to show bijection, so to show that phi is a bijection, there are 2 ways actually. I think it's best for you to learn these 2 ways. Sure. There are 2 ways. Okay. There are 2 ways. So the first way is to show it is onto and 1-to-1. The other way is what? You just find the inverse. Function is invertible if and only if it is bijective. Okay. So either you find inverse, either you show that it is onto and 1-to-1. So we're gonna do these 2 things. Okay, I'm gonna show you these 2 things. Which one is obvious? I guess 1-to-1 is obvious. Why? What's the kernel of this map? E only. I don't know. So you see, kernel of phi is the trivial subgroup by construction. Okay, we define it to be like that. We know that. Okay, so it is 1-to-1. 1 onto onto is what? Onto is what? For every y inside the codomain, we need to find an x such that phi of x equals to y. How many things inside? How many possibility for y? 2, right? If y equals to identity, what's the pre-image? Identity. If y equals to the transposition 2, 3, what's the pre-match? 1, 2. That's all. Okay, now we are checking brute force. We really check brute force. How about inverse? Can you define an inverse or not? So we need a phi inverse from where to where? From 2, 3 to 1, 2. Okay, so let's list down the elements again. So here got identity, 2, 3, and then here got E and 1, 2. So how are you gonna define the inverse map? What do you think? Phi inverse have to be what? Group homomorphism again. E has to go to E, no choice. Okay, if you don't satisfy this, you won't get a homomorphism. At least need to satisfy this. Even if you satisfy this, it won't guarantee you get a homomorphism. But at least you need to do it. So there's only one choice left, which is 2, 3, 2, 1, 2 here. Okay. Okay. So what? So what do you need to check? You need to check inverses got how many property? 2 property, right? You need to check phi inverse is identity, and phi inverse phi is identity. You want me to go through with you, or you can go through yourself? Again, brute force. Brute force again. Okay, because phi inverse start from where? From here. So you need to ask yourself, does phi inverse apply on E, you get E or not? Phi inverse apply on 2, 3, you get 1, 2 or not? Okay. Okay. I mean, right. Yeah. I mean, how about we just draw it out? We just draw it out. I think it's clear. So if you, where do you send E to? If you do phi. So let us make this a little smaller. To do phi, where these go? E should go to E. 1, 2 should go to 2, 3. Okay, this is phi. And if you do phi first, what happened? Who gets sent to E? E, obviously. Who gets sent to 1, 2? Sorry, 2, 3, 1, 2. So if you do, let's write down phi first also. So if you do phi inverse, so you go through these two lines here, you will see that E gets sent to E, 1, 2 gets sent to 1, 2. And then if you do phi inverse phi, you send what? E to E, and then 2, 3 to 2, 3. Okay, okay. So this is the same principle if you're going to a more complicated group. Okay, it's the same principle. Just that maybe when we have a larger group, we don't need to do brute force. Okay, if we need to do brute force, it's gonna be very painful. Okay, when we go to larger group. But in principle, this is what we need to check. Does it make sense? Okay. Do you still have energy to absorb the last thing? Are you guys okay or not? Can stretch a bit more or not? No. Okay. In that case, any question? Any question? Any questions so far? Do you know how to show group isomorphism now? How to build a map? Yeah, you need to construct a map and then show group homomorphism and then show bijective. Any question? Okay, if not, let's take a break until 6:02.这个 homomorphism function function 會 associative。你就係個網嘅。Yeah, sorry. Group element 係呢個。我哋講本身是，因為 function 的 composition 是
我做了一个不数学的归纳法，是不是所有的 order 如果是 n 的话，那么它的 isomorphic class 就是 n 的约数的格式。
n 的什么？
约数的格式。
什么是约那个 factor？
对对对，
是咩？
你检查一下是不是
可是刚才
啊？
不是
除了他自己的 factor 的数量，
对，
你可以 check 一下。
你说这个12就不哦，
1、2、3、4、6，
什么？
这是它的 factor 的数量啊。12的 factor
哦
2、3、4、
，OK，
6，看到没有？4的 factor 只有1和2，然后如果是 prime 的话只有1。
暂时是这样，因为可能啊，
嗯，
可能比如说你的 factor 有4在里面嘛，4里面就包含2个啊，所以它 double up。就是说，
但是12里面有4啊，12也就只有1、2、3、4、6 5个。
对啊，但是可能吗？我就说可能。
所以我说这个时候不完全归纳出来，没有证据，不完全。
我觉得有关系，确实是有关系，因为等一下我们要说这个的时候，确实是跟 factor 有关。有人不是在讲 factor 有关系，
哎，我说都是。
但是我是说，我不确定，我不确定，因为我不是 group theory。对，
你不是什么
啊，group theory
group theorist
就是研究不中，
那你可以研究什么？
我研究空间。
那阿丽啊，专业课吗？
阿里是 graph theory，
对，
懂哎，他都是做 graph 的。哎，来个，这个，就是说，首先，就是说它是 German 来的一个东西，然后我这样的话，你就会知道每一个 group of order P 就是 isomorphic。因为如果它都是 cyclic 的话，你可以照那个 map，就是刚才我所谓的那个 bracket。但是如果你要照那个 map，其实你应该只有一个方法找，就是送他们的 generator 去 generate。因为如果你用其他，如果你把 generator 送去不同的 power，你应该是造不出那个 group of order。需要证明。然后这里的说法是我不需要知道 LOC，但是我不需要知道它 LOC，但是它肯定是新，它肯定是一个东西造出来的。
就个
一是什么？一个 X，就是里面的 element 可以用一个东西来 generate cyclic。cyclic 的意思是用一个 element 来 generate，比如说 Z 可以用 E 来 generate，Z 是个 cyclic group。如果它模的一定是这个，之后不会这。然后如果我知道了，它是 cyclic，then 每一个我的 P 都在那个 cyclic group 之间会有 isomorphic。
那会跟那个
class 的意思就是说，因为他们全部 isomorphic 嘛，他们就活在同一个 isomorphic 的 class。第二个只是说，就只有2个 isomorphism classes of group order 4，所以如果你把所有的 group of order 4的 group 放在一起看，你可以归类为2种，就是这2个。我们等一下会说这2种不一样的线索，不然一样的话没有2种，就1种。所以我们先说不一样啊，不一样过后，然后其实我还要 argue 是全部的都会 isomorphic 这2个，但是应该颠覆一种。 呀，还行，还行，还行，还行。
要几条？
哦，喂，等下我看一下。嗯，
两千。
哦，要不一样哦。
这个是 percent 不是 phi，
对，等一下我看一下。
这个是 percent 不是 phi，
看一下。
PSI。
啊，
暂时先这样吧，暂时先这样。
这个符号要改一下。
是我来改啊，
对对对，
你自己都没有改，你就不要要求他。
暂时先这样，暂时先这样，还可以，可以。
有什么？
没有没有没有没有，只是说我们要不要弄到更美一点，因为那个只是课件上面就方便了
你。有好多 percent 写什么 phi？
OK，那你有改了
没改，
没改？
你还剩好多，你可以去
给他
给他
再改改。
OK。
好了，
马竞
哪一个马军？哦，那你跟他讲啊 ，text height 调一下就可以了，
我们要调成多少？
调多少？没有，要统一。
对啊，我要跟你们统一啊。
你看我
对啊，你跟他讲你的 text height 多少了，
我有调啊，
怎么你会自动呢？
那会看的比较舒服，我的就看的不舒服。
我不懂啊，你就看一下。
这里啊，
OK，let me take attendance。小杨 ，OK，洪杰，哎，子明，
我找个人
子明搞他，
来不了，
子航，Adrian，嘉玲，子轩，李亮，嘉玲，高奇，Eugene，Jasmine，got Albert，got 陈碧，OK，金鱼，OK，金鱼，浩瑞，前面这个 OK，子豪，一层带一层，心仪，心仪，哦，和心仪 OK，修彤，冰夏，小月，子涵，诶呀，雨轩，OK，佳怡，方瑜，王方瑜，not here，王方瑜，哎，方瑜在玩啊，OK，sleeping 啊，佳怡，OK，舒瑶，OK，林夕，云，颜色，一层，Eric，一房，中一房呢，OK，好，若心，看病，怎么你忘记交了他们？OK，赵胜，后来你怎么想起来？Manchun，OK，昊天，why are you absent on the last lecture？哦，休息一下，OK，alright。金星，OK，一航，林一航，哎，林一航是男的还是女的？男的啊，没有在厕所啊？你看到他？他坐哪里啊？他在那个一层旁边啊。哦，没有有人认识他吗？认识我在讲。做那跟你坐这样远的，修着 OK，北刷，康欣，林恩个，伊恩个，正月个，高瑞个，金盆呢？OK，韦德呀，林金个。Hey, anyone is going to the Mugata? Is anyone going to Mugata? 还在想着你有车吗？先，哦，你有车，OK，你回家？I see, right？有家怎么不要回？ 有家才有你，是不是？others 呢？others 呢？正月呢？正月有多应啊？你来看，你做么你也会这样啊？你什么？啊，你太远，你在哪里？啊，住在古来，古来在哪？啊，古来是 JB 的，哎，结婚了，怎么可能？OK，还有呢，道瑞呢？道瑞，哦，你没有车啊？喂，全部不想嫁不是 GG 的。哦，你这样太夸张了，这个可以还好。这样我们应该去蛇湾吃烧鲜。这样吃不好吃哎，不知道哪一间比较好吃，又贵又不好吃。是啊？What？ OK，是哦。OK。If the Chinese students that want to go but really want to go but you don't have transport, maybe you try and contact us. If we got transport, we can fit you in. 你可以先吃一点嘛。我们是志在米丁，不是志在吃，OK？可以先吃一点，如果你5点吃饭这么早，我也是5点吃饭。对，谁不要去？真的啊，人不是没有车了。哦，那不要去，我们就调走。但是他巧去呢，我们又没有车去啊，因为我们是要去那个牡丹的
不要讨论
啊，
这个算了。
怎么呢？他要去，你要去是吗？啊，这样就 OK 了，OK 啊，那我们就 keep 7点半了。哎，摩嘎达的地址可以发一发吗？那个 map， Google Waze， 比较容易找。啊，我不知道。Yeah. So if you are really interested, you can contact us, contact me 啊，繁星or 超奇。等一下，等一下，等一下，不懂我哪一个方便就是哪一个。给我那个 Waze 啊。OK，哎，林恩 going 啊，林恩，you going? Maybe you go car. What? Just now, oh, just now is your car. Oh, okay, okay. What happened? Why? You langgar something? Then how咧? Still can drive or not? But you remove bump, huh? Oh, so are you going or not? Are you going or not, Ling An? Ling An, Ling An, Ling An. So are you going? 就要再看一下。如果你有去的话，你有带谁去吗？谁嘞？Destiny. Okay, good, 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 good. 还可以载人哦。I will still got space, maybe around 5 to 6. If you like，如果延伸要去的话，也可以跟。想去的话可以通知，允许想去也可以通知一下。我们如果安排得到就可以去。我们有车我们就安排一下。不可能有什么自进车呢？有自，什么叫 last call？ 呀、
我讲点到一起，真的驾车人要怎样找那种要被载的人去煮饭
？So we communicate through Teams. If you really want to go, you vigilant a bit on the Teams. We will tag you or you tag us. You say I want go, I want to go. OK， 就主动一点啊，我们大家就主动一点啊，不要这样被动啊，天天叫，天天叫，天天叫这样。我们主动一点，对不对？要去的就大家主动一点，然后被载的或载人的，大家都主动一点。大家想一下，这样啊，如果那个司机要你给油费，或者你觉得不好意思你要给油费，你就给哦。啊，你们讨论一下了啊，要会做人呢。OK。 这种东西是上课学不到的。啊，教完这个，来 ，what time? Yeah, we should start. Right. Okay. So next, let's prove that the Z4 plus is not isomorphic to Z2 cross Z2. Okay, let's prove this. Let's first show that these two are not the same. In mathematics, this kind of negation statement, you need to start with contradiction. Then you need to do contradiction. So suppose there is a isomorphism phi in between Z4 and Z2 cross Z2. Okay, sometimes we short form like this. Okay, maybe a lot of people are confused. 有一个要长怎样呢？不一定要写出来的，我们不一定要写出来的，我们不一定要真正把它写出来。我们要的是 contradict 它的 property。Okay, algebra is like this. You don't always need to write exactly what map, unless I ask you to write the map down. Otherwise, you just use the property of isomorphism. Okay? Suppose there is one, right? Okay, if two things are isomorphic, meaning what? There is a bijective group homomorphism. Okay, suppose there's one. Can we get any contradiction here? Can we get any contradiction here? So to get contradiction here, really you need to understand the group well. Okay, you need to understand these two groups well. So what do you know about these two groups? First of all, their elements. Okay, do you know about how to write down their elements or not? What is that for? 0, 1, 2, 3. Okay, Z2 cross Z2 is what I showed you last time. 0, 0, 0, 1, 0, sorry, 1, 0, and 1, 1. Okay. So if you have a group homomorphism, right, what do you have to satisfy? Okay, in that case, let's list them easier. Okay, you need to tell me where that gets sent. Okay, so there's one arrow get fixed already, correct or not? Homomorphism have to do what? At least send 0 to 0, identity to identity. Okay, so the other map or the other arrow is your own choice. Okay, it's your choice. So how many choices? Let's say if I want to send one, there are 3 choices. So if we're gonna do contradiction, meaning what? I need to contradict all these 3 choices. Okay, all these 3 choices doesn't work. Doesn't work. Okay, so let's try. So assume for contradiction. Suppose phi1 equals to 0. Okay, any contradiction? Any contradiction or not? What else you can play around here? How about consider phi1 plus phi1? Let's do it. So if we do consider, we play around with this map, just using phi1 plus phi1. Okay, what do we get? On one side, we get 0, 1 plus 0, 1, which is 0, 0. But you know that this is a homomorphism, right? Phi1 plus Phi1 also equals what? Phi1 plus 1. Meaning what? You have to send your 2 to 0, 0. No choice. Oh. This one is by group homomorphism. If you fix where you send your 1. How many things get sent to 0 in this case? 4. 2, right? The identity ends 2. So now, P sends both 0 and 2 to where? To 0, 0. Meaning what? Meaning P is not injecting. Okay, so we have a contradiction. And by the way, this is shorthand. Don't learn me like write in your assignment so contradiction. So we reach a contradiction. Oh, yeah, fill in the blank. Okay, so there's a contradiction. Okay, so we cannot send 1 to 0, 1. Then we send to 1, 0. Okay, then we send to 1, 0. What happened? Can you imagine if I replace this number with 1, 0? And then we got 1, 0 plus 1, 0. Again, 0, 0. Again, P2 gets into 0 again. Again, contradiction. If I send to 1, 1, also the same. Can you think of why they use the same argument? So meaning if they are the same, I can replace this argument abstractly by what? I can send Phi1 to Y in Z2 cross Z2 such that this Y is not equal to 0, 0. And then the whole proof follows. Why? 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 What does it mean by you add twice, you get 0? This means what? The order of Y is 2. So meaning what? All the elements other than 0, 0, the order of the elements are 2. Yeah, so the order of elements, order of 0, 1, 1, 0, 1, 1 are 2. So if you do Y plus Y, you will always get the identity. Okay, but on the other side, what's the order of 1 here? Order of 1 is what in Z form? How many times you add to yourself, you get 0? 3 times, but you add 4 of them, right? So the order is 4. Okay. Yeah. Does it make sense? So meaning Z4 has an order 4 elements, and then Z2, all of them are order 2. So they cannot be isomorphic. So there's some clue for you to see how to get isomorphism or how not to get isomorphism. You can look at their order of elements. Okay. Right. Yeah, question? Any question? Question? So similarly, we get contradiction if phi sends 1 to 1, 0 or 1, 1. Okay, so in all cases we get contradiction. Any question? No, we don't have a isomorphism between them. Okay. Okay. So there are 2 ways to write these, right? So either you write down all the possibility, or you just you send to some element inside Z2 cross Z2, which is not the identity element, and then you figure out that all the elements there has order 2, and then you use this contradiction. Okay, good. Should we go back to discuss this example again a little bit deeper? So, in these three examples, right, we know that they are group homomorphism already. Okay, we know that they are group homomorphism already. Correct? For exponential math, you know it is a group homomorphism because e to the xy, x plus y is ex times ey. And then second, what is n plus m here? You will send phi n plus m to phi to the power n plus m, which is phi n times phi m. Okay, group homomorphism. Here then, here is an homomorphism by construction. It's by construction here. Okay. So remember this example or not inside your assignment 2. Okay, how we attach a permutation to a permutation matrix. Okay, we see how the permutation permute the n indexes. We also permute the n standard basis. And then we figure out the permutation matrix. So the only thing left to show is they are bijective. Okay, why are they bijective? So for the first one, you know the inverse or not? What's the inverse of E, as I mentioned? Logarithm. Okay, natural logarithm. Okay. I think in the when you do MA later, how we define is we define logarithm first. Okay, we define logarithm as the integral of 1 over x. That's why you integrate 1 over x, you get ln x. That is definition. So that's why we take it as a formula for your high school, because we define it like that. Okay, it's a ODE that equals to 1 over x. Okay, ordinary differential equation equals to 1 over x with some boundary condition. And then we define E as an inverse of this ODE. Okay, so they are inverses of each other. Second, this one too, how to go take inverse? Quite obvious, right? If you can take n to a power of n, what do you do in cyclic group? You can write everything as a to some power. So you just send the power back to integer. And then here how to do it? Here a bit trickier. Left as a sign. Okay, I'll write down for you, but try and think about it. Okay. Left hand as a sign. Okay, I will write down and then you'll try and think about it also. I'll left it in the lecture note. Okay. Good. So I think before we end, we're gonna prove a pretty hard theorem now. And this theorem will demonstrate to you why Sn is super important. So this theorem bears a name. So you need to be careful when a theorem bears a name, because this means that this theorem is super hard to prove. And then this guy proved it. So this is the Kelly's theorem. Kelly's is a group theorist. So he proved quite a lot of property or theorem in group theory. So we're going to prove that every finite group is isomorphic to a group of permutation. Do you still remember what does a finite group means? Finite refer to what? How many elements inside the group? So how many elements inside the group? It is finite. Okay. You can count. Okay. So if you have a finite group, it is isomorphic to a group of permutation. Meaning what? Meaning you inside this group there are permutation. It could be a subgroup of Sn. Okay, different n. It could be Sn, could be subgroup of Sn. Okay. Yeah. Right. So please follow. This both a bit involved. So okay, let's pansing first. If you want to show isomorphism between these two groups, what do you need to do? You need to construct 讲，要害羞。What? What do you need to construct? If you want to show two group is isomorphic. Isomorphic. Isomorphic needs what? Isomorphism. Isomorphism is what? Is a 来子轩要不要救救他 ？Isomorphism is what? A function. What kind of function? Bijective and group homomorphism. So first you need to construct a function first. So let G be a finite group. Okay. So what we're gonna do, we're gonna define a map from G to SG. Okay, so what's this SG here? This means we want to permute. So let me write here. So we want to permute elements of G. Okay, or what? Or later you will see this. This is actually isomorphic to X of the element of G. Okay. So meaning what? You are permuting n things. Okay, so let me add something here with order absolute. Yes, that's right. So here, when we think of SG here, we are permuting G elements. But here, when we write it here, this is what? Modulus of G is some number. So meaning we permute indexes. So meaning what? We form a bijection between index and group element. This is like standard basis. No? We form a bijection between n indexes with n standard basis. But here, we form it with group elements. We replace standard basis by group element. Does it make sense? Okay. Or question? Or you need an example to imagine. Need example. Okay. So, right. Cool. Okay. So let's G equals to this E and 1, 2. Okay. So how to permute these two things? Is the same group. Okay, it's the same group to permute these two things. But what is S of modulus G here? It is just S2. Okay, because what? Because what you really do in your brain, you maybe draw this arrow. So you associate E to 1 and then associate 1, 2 to 2. Okay. But this is like what we do. This is really like what we do for the Sn and Pn isomorphism. We send 1 to E1, 2 to E2. So what's the group that permute G? You can fix E1, fix 1, 2, or you exchange them. That's all. Okay. Later I'll tell you why we do this, but just follow first. Okay. Later we'll see how it works. Okay. So to be precise, really precise. So I need to tell you what this map have to do on my element. Okay. So meaning if I give you a element in the domain, what happens? Okay, we send it to a permutation. Okay, that is called lambda x. So what does this lambda x do? So let's move this example down. So what does this lambda x do? Okay, again, slowly a bit. So we have an element in this group. We want to map it to a permutation. Okay, permutation here means what? Again, group a bijection is another map. So meaning we send x to a map which is a permutation. Permutation is what? Another bijective map. Okay. So we actually need to argue why this map is bijective. So what's this map here? Again, map or what does this map do? Sends element in G to G. Okay. Send element in big G to big G again. So how to do that? Again, I need to tell you what happened to every element inside big G. Where do I send it? I send it to X times G like that. Okay. So a bit confusing is when we define a map, actually we send element to function again. Okay, so this is a little bit confusing point. But it is not confusing at all if you know that what is FG. So what is FG? Set of permutation. What is permutation? Bijective map. So I define a map for you. Obviously, I need to argue why this map is bijective. Why live inside this set here? Does it make sense? So to argue that lambda x live inside SG, I just need to argue why this map is bijective. Because this is a definition of permutation. Okay, permutation by definition is bijective. It's just bijective. Okay. Permutation of n indexes meaning bijective map between n indexes. Okay, this is definition. Okay, so let's tell you the name first. This name is called which is called the left regular representation of G. So why is it left? Because we multiply x from the left. So you could imagine we can do a right one. Okay, later you will try. You can try yourself, go through the whole argument using G to Gx, for example. Okay, left regular. So obviously, if I do this map, first of all, I need to check that I land in the right moon. Right or not? If I land in Saturn, then I'm false. So how to land in the right SG? We first have to verify that lambda x is actually a permutation. Okay, we need to make sure that it is a permutation first. We need to make sure we land in the right codomain. So to prove that it is a permutation, what do you do? Two ways. Again, just now I told you, right? Two ways to show bijection. 1-to-1 onto or inverse. Okay, now I think I will do 1-to-1 onto first. Inverse, maybe I leave it for you. So two things to check. So you need to check that lambda x is 1-to-1, and then you need to check that lambda is 1-to. Okay. So how to check on 1-to-1? Spell out the definition, like what I told you in algebra. Just spell out definition, answer will almost drop out. Okay, so what is 1-to-1 means here? If lambda x y equals to lambda x z, we want to show that y equals to z. Okay. But what? But lambda xy equals to lambda xz is what? By definition. How do we define lambda x? Send g to xg. So meaning I send y to xy. I send z to xz. Then what can we do? We can use cancellation law such that we get y equals to z by cancellation law. Because x is an group element. Okay, it's invertible. Okay, y equals z, good. Onto it, meaning what? For every element inside my codomain, I need to find an element in the domain such that L x equals to G prime equals to G. Okay, a bit confusing here because our domain and codomain is the same. Okay, because it's a map from G to G. It's a permutation of G. Okay. So how to find if you have a G, okay, what you need to plug for G prime such that SG prime equals to G. You see, What do you need to choose for G prime such that you get X G prime equal to G? Right, let's put our goal here first. X G prime equals to G. So have to pick one. And one thing you need to put inside here. When you multiply with X, you get G. Everyone else also think, what thing you need to pick here to get G? What do you need to take? Obviously, because X is coming from G. 没有，我们的 obvious 是没有骂人的，没有带脏话 ，obvious 是真 obvious。Gone 了，哦，一凡，你看我了 ，even，no need to look anywhere else there, no need to look anywhere else there, just look at here only. So given G, what G prime you can pick? Only looking at here, no other prior knowledge you need. Just here. Something that you multiply X, you want to get G. Huh? Ifan can help. Want to try? Very sure. G prime equals. So what G prime we can pick here? X is fixed, G is fixed. X equals G, right? Why? Since what? Since X times X inverse G is what? By associativity, you get identity times G, which is G. So lambda X G. Okay. Okay. X inverse exists, right? Because it's a group element. So therefore, good. So therefore, we can conclude for the moment, this lambda X is really an element in X of G. All right. So what else we need to check? We just check that whether we define a proper map or not. What else we need to check? We need to check the phi here is actually a group homomorphism and bijective again. Wow, so many bijective need to show. Okay. Yeah, so this means what? Bijective is very important in this class. Okay, so you have to definitely learn it. So next, what else we need to show? We must show that this phi is a group. Verify. Phi is a group homomorphism. Right. Should we do this first? Let's do this first, okay? So let's do this. So take xy in G. What happened? We want to show what? Lambda xy equals to lambda x times lambda y. Okay. But what kind of equality is this? This is function equality. So to show function equality, you need to do what? You need to check on every element in the domain. Okay, so take any elements in your domain. Okay, what do you need to do? Compute lambda xyg. So what is lambda xyg by definition? Xy times g. Okay. What's your goal? Maybe I forget my goal already. So what's my goal? Lambda x dot lambda y times g. What does it mean by composite function apply on g? Meaning what? You apply which one first? Lambda y first on g, and then you apply lambda x. So if you spell this thing out, what do you get? You apply yg first, and then you apply x. But what do you have on the other side? You have xy times g. On the other side, you have y times x times yg. But why are they equal? Associativity. Good. Yes. Okay. So we are really using group property here. Okay, well, actually these homomorphism drop out from the group associativity. Right, so we have shown that group homomorphism. Next thing is, let me tell you a lie. So I lie to you that we want to build a isomorphism here. Actually, it is not. 不要紧张，不要这样紧张，不要紧张，不要紧张，不要紧张。So, although it's not isomorphic to this xg, but it is isomorphic to something inside this xg, which is a subgroup of this xg only. Okay. Make sense? Okay, so no what? So I mean, okay, so let me be precise. What I want to say is this phi g here, okay, it will inject into this SG by the image of G. Okay, so this image of G here, what we can really show is a subgroup of G. That's all. Okay, we won't, the image of G won't always fill out the whole group of permutation of group M. Okay, so let's continue. So what we only show is, we will only show that we will only show that phi is 1-to-1。不要紧张啊，等一下我还再讲一次啊，不要紧张，先跟先。OK， 不要紧张啊。So 1-to-1。Okay, so how to show phi is 1-to-1? A very good, sorry, yeah. So how to show is 1-to-1? Two ways, right? You can show from definition, okay, or you can show from kernel. Okay, let's do the kernel way. So we need to show that. We just need to show that is kernel of phi is identity. Okay. So if we want to show this kernel thing, meaning we need to show set wise equality here. So what's the set wise equality here? So there are two directions, right? You need to show that the trivial subgroup is inside kernel of phi, and then the other one is kernel of phi. Sorry, phi is in the trivial subgroup. Okay, so let's see. So what does it mean by identity element is in kernel of phi? Meaning what? You send phi of E to where? To lambda E. Okay. And then you need to show that this lambda E is the identity inside your group. Okay, so is this, so the question is whether this is an identity inside your group or not. So identity inside your SG. Okay, so to check that this map is an identity map, what do you need to do? You just apply this map to every element in the group. Okay, so for every G in G, so what happened to LEG? LEG is what? Is EG. EG is what? G. So meaning what? Meaning this LE send every G to G. So meaning what? This LE is a identity inside the SG. Okay. Okay, please follow. Okay. So this says that LE is the identity permutation in SG. Okay, so it really sends identity to identity. Okay. How about the other way? If there's anything in this SG, if there's anything in this kernel, it must be the only LE is the only map that sends G to G. Okay. So let's do it. So suppose S is not the identity element in the kernel. Okay. But we require what? Require that lambda x. We require what? We require that lambda x. What's the kernel of this one? But require that. Require what? I'm confused now. So we require what? What's being the kernel of E here? What's the condition here? We need to send. Sorry, let me go back a bit. So we need to send phi x to the identity element inside SG. Okay. Yeah. Okay. But what does this mean? This means what? This means lambda x has to be identity of SG. Okay. Agree? Agree? Okay. Agree. So how are we going to show this? So how are we going to show this? So from here, we want to deduce that this S has to be E. Yeah, from here, because this is the property of kernel, right? Then phi send X to the identity inside the group. But what's the phi X? We define lambda X. Okay, but how does this determine that this X is E? So a very clever choice is look at what does lambda S does to identity. Okay, a clever choice is to do this. So let me remind you, for the identity in G. Okay, so what happens? So what does this map does to E is identity of this E. So if you have an identity permutation on E, you will get back E again. But on the other hand, how do we define lambda X? We define it to be X times E. So meaning what? These two have to agree. Okay. But if X equals to E, what S can be? Why? Because the inverse of E is E. The inverse in the group is unique. Okay. So by uniqueness of inverse of E, X has to be E. Okay. So all together, what do we get? So all together, we have phi that maps G injectively to phi G. But phi G is what? We prove that image of a group is always a subgroup. Okay, so this is a subgroup of the permutation group on G elements. Okay. So what we really show is we only Okay, we have injectivity of image, right? At the same time, this map is what? Is onto the image. Because everything in the image I know must be coming from something in the domain. Okay, so you get surjective for free. Okay, so for free. For free, you have onto. Okay, yeah. So actually, it only isomorphic to some subgroup inside the group of computation. Okay, and this is always the case. Okay, so this is always the case. So if you apply the isomorphism that I told you just now, right? This means what? Every finite group is isomorphic to some subgroup of Sn. Where do you find this n? You can construct this n from the group of elements in G. Any question? Question? No? Sorry. Right. Yeah. So I mean a very good exercise, see if you can do the right regular representation. Repeat whole proof using right. Instead of G to SG, you do SG to GX. Okay, see if you can do the same way or not. Okay, a very good exercise to repeat this proof. And there are two remarks to say before we finish. Then next time we go to a coset. Okay, next time we go coset. But this time this result, right, should be Bremenizing to you to this multiplicative table here. Okay, meaning what? Why last time I told you that in the every row and column you won't repeat your elements when you multiply. It's exactly because they are doing permutation actually. Permutation of group element when you multiply. Correct or not? Just now we do G times SG, right? So S times G, S times G, S times G, S times G, S times G. All the S times G is here. So multiplication table is the list of left regular representation. Does it make sense? So how about I write it down a bit clearer? So for example, let's look at this case here, 2. So where's the x? X is here. So there are x1, x2, x3, x4. And then here is g1, g2, g3, g4 here. Okay. So for every x, you define lambda x. Lambda x. Lambda x1, lambda x2, lambda x3, lambda x1. Okay. So really it's a computation. See? Does it make sense or doesn't make sense? And if it doesn't make sense, please speak up. Okay. So if you do right representation, meaning what? You see from the other side, here or not? Your S becomes here, and then your G becomes here. You go this way. GX, 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 GX. Okay. So the left representation and the right representation. Okay. Does it make sense? Okay. So it's not a coincidence why you see distinct group element appearing in every column and every row, because we proved it just now. Multiplication by a group element is a permutation. It's a permutation. See, if you take 0, multiply them, okay, keep them. But 1 permutes off. Okay, 0 go to 1, 1 go to 2, 2 go to 3, 3 to 0. Okay, if you take 2, apply on all the group elements, then 0 to 2, 1 to 3, 2 to 0, 3 to 1. So it permutes. Permutes. Can follow? Okay. Yeah. And one last remark I want to leave to you is, so let me write it down here. So let me remark here. Okay, so let me write down the abstract statement first. So it is possible that G is isomorphic to some other thing inside SG. Okay, I mean, this is the phi that I told you. Okay, let's write down phi then. This one is defined to be phi. How about phi of G, which is living inside SG, but this SG is x to the number of group element. But at the same time, this G PG prime could be isomorphic to something else, such that this G prime if live in a smaller Sn. Yeah, I give you an example. Okay, I give you an example. So I give you an example here. So for example, a finite group is Z6. Okay, so based on the proof that I gave you just now, where should I find the isomorphic image? Which Sn I need to find? I need to find a subgroup inside S6 because there are 6 elements there. So I mean, there's one choice I can make here. You can make any choice you want, okay? But this is the choice I'm gonna make. So I'm gonna make a choice which is a cyclic subgroup generated by 1, 2, 3 times 4, 5. Okay, so disjoint cycle. So let's verify this. Okay, let's verify this. Okay, let's verify this. Do we have this isomorphism or not? So what do we do? Again, last time I will ask you already, was to how to find isomorphism between two groups. Let me ask someone. Sorry, 小月. 2月. Okay, 小月. How to find isomorphism between Z6 and this cyclic subgroup? Fine. How to find? I mean, I don't know. How? Wait, sorry. Let's take back. Okay, so how to show there's isomorphism between Z6 and this cyclic group? Good, very good. So, meaning what? Let's write down all the elements on both sides here. Let's write down all the elements here. So, on Z6 got how many things? 0, 1, 2, 3, 4, 5. How about this cyclic subgroup? So, this cyclic subgroup here contains what? What does it mean by group generated by this disjoint cycle? You keep composing 1, 2, 3, 4, 5. Keep composing. Okay, keep composing. Okay, can I do it very quick? Let's do it very quick. You go back and verify. I quickly compute. Imagine I have a supercomputer. Okay. So, okay, go back and compute. Take power of 2, 3, 4, 5. So power 1, power 2, power 3, power 4, power 5. Is it correct or not? Go back and check. Okay. So the map I'm going to make here is 0 to identity, and then 1 to this guy, to this guy, to this guy, to this guy, to this guy. And then you can verify that this is a homomorphism. And then this is a perfectly good bijective, right? Because identity to identity, and then everyone has an inverse. So only thing you need to check here is group homomorphism. Okay. But this cyclic subgroup can live in a smaller Sn. What is it? This cyclic subgroup can live in a smaller Sn. You can live in X5 actually. So the proof just give you a larger choice. Actually, the thing that you are isomorphic to can be found in a smaller N, in principle. But it doesn't matter because our result is just to show that every finite group is isomorphic to some group of permutation. I don't care where it lives. Okay. Does it make sense? It doesn't make sense. Why? Why doesn't make sense? It doesn't make sense. You have to say why. Very important. Huh? Why? 等一下 ，OK，等一下，可以。Okay. Yeah. Okay or not? So the proof only give you isomorphic to a subgroup where the n is equal to the cardinality of the group. But maybe you can find it in a smaller n. Does it make sense? Understand? Can find it. Yeah. Any question before we finish? Okay, so there's some admin announcement. I think after we finish assignment 3, then we need to prepare for our midterm. Okay, the test will be, I think, until around assignment 3. I will confirm the scope again. And so our midterm is happening at week 9. So we could do revision if you want, either week 7 or week 8. Okay, depend on how we finish our assignment 3. During that revision, okay, we could discuss all the tutorial questions before. Okay, so I need you to try to do tutorial question first, and then you can bring question to the revision session, and then we can discuss, go through detail. Okay, we can go through detail there, okay, bit by bit. And then we also can, I will give you practice exam question also, you can do it. We also can discuss during that revision session. Does it make sense? Does it make sense? So to do this, I want you to try the exercise first. Okay? No need to finish all day by day, finish a bit, it's fine. Okay? But until that day, hopefully you have some question to ask. Make sure you ask question. Question is very important. All right, if there's no more question, we'll see you next week. For those who have the lecture notes, typing lecture notes, please stay back. Yeah. 等一下哦。呀，莉莉亚，怎么样？